पड़ती नहीं इसमें।
तो सर वहीं पर आ रहा होगा बटन सबसे लेफ्ट साइड में जो बटन है यहाँ पे म्यूट लिखा हुआ है उस पे, उसी पे कर दीजिए, अनम्यूट म्यूट लिखा होगा सबसे लेफ्ट साइड में सर। वीडियो
आपकी आवाज तो आ गई, आपकी आवाज आई है।
हाँ बस तो सर आप भी बोलिए, आपकी आवाज भी आ रही है हमको, आपकी आवाज भी क्लियर है।
अच्छा तो ठीक है, फिर आपकी आवाज आने लगी मुझे।
सर आपकी भी आ रही है
तब ठीक है, देन लेट्स गो।
यस।
अभी ये पूनम बोल रही थी तो आवाज नहीं आ रही थी मुझे।
नहीं, उन्होंने बंद कर रखी थी आवाज।
अच्छा ठीक है, तब ठीक
म्यूट पे है, वो म्यूट पे है।
बस मेरी आवाज आपको मिल जाए इतना काफी है।
जी सर, बिल्कुल क्लियर आ रही है आपकी आवाज सर।
बहुत बढ़िया, वेरी गुड।
गुड मॉर्निंग।
गुड मॉर्निंग सर।
गुड मॉर्निंग।
गुड मॉर्निंग। कैसे हैं प्रोफेसर राजपूत? आई एम अजॉय खट्टर।
अच्छा लग रहा है आपसे बात करके।
राजपूत सर नमस्कार।
नमस्कार।
एमएस भंडारी दिस साइड।
हाँ भंडारी जी, आपका नाम दिख रहा है, अच्छा लग रहा है देख।
राजपूत सर गुड मॉर्निंग। आर के तिवारी दिस साइड।
हाँ तिवारी जी नमस्कार, हाउ आर यू सर?
गुड मॉर्निंग।
आई एम फाइन सर, योर ब्लेसिंग्स।
घटक सर नमस्कार। घटक सर नमस्कार।
नमस्कार नमस्कार नमस्कार। Good to see you all. Good to see you all.
Thank you, sir.
Gatak sir, namaskar
For joining us. Gatak sir, thank you for joining us.
अरे नहीं।
सिंगल साहब।
जी सर।
सिंगल साहब
जी सर।
राजपूत सर नमस्कार।
Very good morning to all of you, sir.
Oh, Yogesh, good morning.
Namaste, sir. Professor Nityan, sir. Namaste, sir. Good morning.
वाशने सर गुड मॉर्निंग। आपकी आवाज चेक कर लीजिए, आ रही है नहीं आ रही है वाशने सर?
A warm welcome to Professor Rajaram Nityanand, PN Varshne sir, Padma Shri Professor J.S. Rajput, and Professor Ajoy Ghatak, and rest of the professors who have joined us as a panelist. A very good morning to all of you.
Good morning.
Professor Mani has also joined.
Mani, good morning.
I have joined. Yes. Hello.
YouTube कहीं और खोलो.
Video of Professor Mani.
Yeah, that's fine.
Yes. Okay, sir. Okay.
All right.
Okay. Welcome, sir. Welcome.
Thank you.
दिखाई नहीं दे रहे सर।
नहीं दिखाई दे रहे अभी तो, अभी शायद आप।
वार्षणे सर गुड मॉर्निंग।
आई थिंक उनका ऑडियो कुछ कनेक्ट नहीं हो रहा। वाशने सर।
हाँ उनका ऑडियो कनेक्ट नहीं हो पा रहा, जरा देखो।
वाशने सर नमस्कार।
नहीं जा रही।
नहीं आवाज नहीं।
घटक सर नमस्कार।
नमस्कार जी नमस्कार।
Sir, he has connected from our side. Sir, Varshne sir has joined from our side. There is some issue from the. हाँ, there is issue from his side.
ऑडियो का प्रॉब्लम है कुछ उनका।
मैं उनको बता देता हूँ।
सिंगल जी आपके पीछे क्या है? ये तो बड़ा सुंदर फोटो है।
सर आप तो जाते रहते हैं, मैंने कहा मैं भी थोड़ा कोशिश करता हूँ। आई ट्राइड, थोड़ा मैंने उसको चेंज कर दिया, बैकग्राउंड को चेंज कर दिया मैंने।
कैसे किया चेंज?
सर यहीं पर ऑप्शन आता है आपके इसमें ना, जहाँ पर आपका जहाँ वीडियो होता है वहाँ पर ऑप्शन आता है। यू कैन पुट योर बैकग्राउंड एनीथिंग व्हाटएवर यू वांट।
ओह आई वुड लाइक टू।
I don't mind, sir.
दिस इज वर्चुअल बैकग्राउंड।
ओह आई सी। तो उसको क्या राइट क्लिक करके?
सर उसमें हाँ, उसी पर ना वीडियो वाले पे आप क्लिक करेंगे एरो पर।
टॉप वीडियो पे सर।
हाँ टॉप वीडियो वाले पे क्लिक करिए।
अरे वाह, आप तो
एरो पर क्लिक करिए।
नहीं वीडियो पर क्लिक करता हूँ तो क्रॉस हो जाता है। अच्छा एरो पर
करिए।
एरो सर मार्क
चूज वर्चुअल
बैकग्राउंड राइट।
मैं कुछ दे रखे हैं, सेलेक्ट कर लीजिए।
जी सर।
350 people have joined, so we may start at 11 sharp.
Yeah sir.
Yes, wait for 2 minutes sir, please.
Okay. We start at 11 sharp.
यहाँ तो वर्चुअल बैकग्राउंड कुछ है ही नहीं।
सर सेलेक्ट करिए उनसे।
होगी सर।
सेलेक्ट करिए सर।
वीडियो में एरो अप एरो क्लिक करिएगा, उसमें वर्चुअल वीडियो का ऑप्शन आएगा,
वर्चुअल बैकग्राउंड का।
हाँ हाँ सर,
हाँ सर, हाँ
उस पे लिखा है नन, चूज
नहीं,
वर्चुअल, अच्छा
choose-
प्लस,
इसमें आ रहा है
हाँ।
चूज वर्चुअल बैकग्राउंड,
यूज वर्चुअल बैकग्राउंड लिखा है ना सर।
उस पे आइए आप।
इस पे नहीं है, चलो कोई बात नहीं, आई विल डू दैट नेक्स्ट टाइम।
अनिल सर गुड मॉर्निंग।
भाई साहब गुड मॉर्निंग। अनिल जी, अनिल
नहीं,
भाई
उनकी
साहब,
उनकी उनकी ऑडियो बंद है।
ऑडियो वीडियो भी हाँ सर, नमस्कार।
गुड मॉर्निंग, नमस्कार सबको।
गुड मॉर्निंग सर।
गुड मॉर्निंग सर।
गुड मॉर्निंग।
A very good morning to Srivastava sir and all the respective professors and teachers present here. Sir, technically everything is ready from my side, and as I can see, approximately 300 plus participants has joined us. So sir, if you permit me, may I start the formal session for the day?
Yes, please. Yes.
Thank you sir, thank you so much.
Yes, please.
A very hearty and warm welcome to our distinguished speaker, guest of honor, respected panelists, and dear participants. Myself, Poonam Jain, Executive Council member and your host, welcome you all for the first session of the online webinar series organized by IAPT RC1. Before beginning with the formal session, there is an important announcement for the participant. This session is being recorded and live streaming on YouTube and Facebook. All the panelists are requested to kindly mute their mics. Now, I would like to hand over the session to Dr. S.K. Singhal for the formal proceedings.
Thank
Dr.
you, ma'am.
S.K. Singhal, over to you, sir.
Thank you, ma'am. Good morning, all professors, panelists, and the participants. Myself, Dr. S.K. Singhal, Treasurer IAPT RC1, Delhi, Haryana. Welcome to all of you in the IAPT online lecture series of wave optics by Professor Rajaraman Nityanand. This program has been organized in the collaboration with the Delhi State Science Teacher Forum. For certificates, attendance is mandatory in Google form. The link of the Google form will be shared in the chat box and YouTube. The participants are also requested to post their questions in question answer box only. Do not post in the chat box. Those are unable to join through the Zoom, they are requested to join through Facebook or YouTube Live. They are also requested to write their name and email in the comment box. Now I request Dr. M.S. Bhandari sir, Secretary IAPT RC1, to deliver welcome address and give introduction to our guest, Padam Shri Professor J.S. Rajput. Bhandari sir.
Good morning, everyone. Indian Association of Physics Teachers, a major and well-reputed organization established by late Dr. D.P. Khandelwal in the year 1984, has local chapters in every state. IAPT RC1 is chapter of IAPT for Delhi and Haryana. We organize various activities for promotion of physics and physics education. Today's lecture is a part of this mission. Here is another for us to give an opportunity to our distinguished speaker, Professor Rajaram Nityanand, and under the able guidance of respected Padma Shri Professor J.S. Rajput. Padma Shri Professor J.S. Rajput is a well-reputed reformist in school education, in teacher education, and institutional management. He was a professor of physics, NCERT, and principal of Regional Institute of Education, Bhopal, from 1977 to 1988. He has held the prestigious post of Educational Advisor, Ministry of Human Resource Development, Government of India from 1989 to 1994. He has served as the first chairman, National Council of Teacher Education from 1994 to 1999 and the director of NCERT from 1999 to 2004. The innovative idea of starting the 2-year B.Ed course in 1999 goes to his credit. He chaired the groups responsible for preparing National Curriculum Framework for Teacher Education in 1998 and for his school education in 2000. Padma Shri Professor Rajput has been closely associated with various international agencies for over a period of 3 long decades and continues to be active presently. Government of India has nominated him as member of Executive Board of UNESCO. In the year 2004, UNESCO acknowledged the outstanding contributions by Professor Rajput in research and innovations by selecting him for the prestigious Jane Amos Comenius Medal. The Government of India bestowed over him the nation's prestigious civilian honor Padma Shri in 2015 in recognition of excellent and path-breaking contributions in the field of literature and education. On behalf of IAPT RC1, I welcome Padma Shri Professor J.S. Rajput, special guest of honor for this lecture, and distinguished speaker for today's assembly, Professor Rajaram Nityanand. I welcome Sri Kanhaiya Lalji, Sri P.N. Vasudev and other executive members of Delhi State Science Teacher Forum, Physics Faculty of NCERT, Physics Faculty of Delhi University, teachers from different institutions, nation and abroad. Participation of physics fraternity in large number is gratifying and motivating. A warm welcome to all of you. Now may I request Padma Shri Professor J.S. Rajput to kindly address the participants. Thank you, sir.
Thank you, Bhandari sir. Now I request Padma Shri Professor J.S. Rajput sir to deliver the address. Rajput sir. Sir, you are muted. Kindly unmute yourself.
I've done it. Is it okay now?
Yes, sir.
Yes, sir, it is fine now.
Yes, sir.
Okay. Thank you, Professor Singhal, for the kind words. I'm extremely happy to be in the company of Professor Rajaram Nityanand, Professor V.P. Srivastav, esteemed professors, colleagues, and friends. I have on the YouTube seen the lectures of Dr. Aswal and Professor Ghatak, and that has created my interest in these activities. Someone like me would certainly like to recall his long association with IAPT, and I particularly recall Professor D.P. Khandelwal when he was initiating the whole process, and I also recall Professor Saraf. These two eminent persons, in fact, created my interest in popularization of science, and it resulted in creation of 3 science parks, one in Bhopal, another in NCERT, and the third one in the National Balwan Society of India and Kotla Road. Essentially, my discussions with Professor Khandelwal were focused mainly on how conceptual clarity can really be obtained and imparted to children at the earliest in their sensitive years. That is what finally matters. I would quote an instance of one of my professors who taught me in Allahabad and later on went to Varanasi. He said, I had taught you religions law. I did not understand it. Neither you understood it. All of you also didn't understand it. I got it really clarified after 7 years from Professor so-and-so. This is happening in many places. And we have to be very, very careful about it. That is how I'm looking forward to listen to the lectures of Professor Rajaram, because to a person like me who has not been very active in physics for all these years, this would be a process of relearning. When I heard that he will be speaking a next lecture on polarization, I was reminded of Richard Feynman. When he went to Brazil and later on wrote about his experiences, he refers to polarization, and he says the students could answer all these straight questions, but they did not know how to apply what they had been taught. And this is what the difference, what Feynman said. This is the difference between the way they learn physics in America and the way they learn physics in Brazil. That is still happening in our many places. And that is what is the challenge before such luminaries like Professor Rajaram, Professor Aswal, Professor Ghatak, and Professor Srivastava. How do we prepare teachers who would really be very efficient, who will really know what is the conceptual clarity, how it is obtained, how it is pedagogically transmitted, and how the utility comes back. Let me close by making one remark that you see, Bertrand Russell once wrote that you cannot depend only on knowledge. Knowledge was at its peak when in the last Alamos in 1945. But there was no discrimination. Buddhi was there, Vivek was not there, Hiroshima happened. Therefore, apart from knowledge, concept, clarity, the appropriate utilization is the most important factor. This is what we have to achieve through IAPT. This is why I understood. I pay my tributes to those stalwarts who have all along established a prestige and credibility for the IAPT for this chapter. And I assure you, I would always take the benefit of being associated with you, with Professor Srivastava, Dr. Rajaram. Professor Ajay Ghatak has helped me very much when I was in NCRT. And I hope I would be benefiting myself by association with you. Thank you very much.
Thank you, sir. Thank you, Professor Rajput, for your valuable word. Now I request Professor V.P. Srivastava, sir, President IAPT RC1, to introduce the distinguished speaker of today's lecture, Professor Rajaram Nityanand ji. So I request again, Srivastava, sir. Sir, you are muted. Sir, kindly unmute yourself.
Namaskar. Good morning, everyone. It's my pleasure and honor to introduce today's distinguished speaker, Professor Rajaram Nityanand. I first met Professor Rajaram Nityanand in 1995 in the Indian Institute of Science, Bangalore, while I was working to finalize the manuscript of NCERT Class 12 Physics Textbook under the chairmanship of Professor T.V. Ramakrishnan. That time, Professor Nityanand was working in Raman Research Institute. Professor Rajaram Nityanand did MSc in Physics from Indian Institute of Technology, Madras, and PhD from Bangalore University, working under Professor S. Ramaseshan at the Material Science Division of the National Aeronautical, now Aerospace Laboratory, on optics and crystallography. He was a professor at the Raman Research Institute before taking up the position of Center Director, National Center for Radio Astrophysics, Pune, a center of Tata Institute of Fundamental Research, which he held till 2010. He then served as Center Director, TIFR Center for Interdisciplinary Sciences, Hyderabad, from March 2011 to June 2012. From March 2013, January to 2014, he was a visiting professor at the Indian Institute of Science, Education and Research, Pune, and he is currently with the School of Liberal Studies, Azim Premji University, Bengaluru. Professor Nityanand has research interest in solid-state physics, liquid crystals, astronomical optics, image processing, and gravitational dynamics. He has been editor of Pramana, Journal of Physics, and Journal of Astrophysics and Astronomy, and the editor of Resonance, a journal of science education. He was a member of the International Steering Committee of the Australia Telescope National Facility. Professor Rajaram was also the chairman, Board of Governors, NIT Tiruchirappalli. Professor Rajaram is a fellow of all the three National Academies, Science Academies of India, namely, he is a fellow of the Indian National Science Academy, a fellow of the National Academy of Sciences, and also the fellow of the Indian Academy of Sciences. Professor Nityanand received the K.S. Krishnan Memorial Lecture Award 2004 of INSA. His extended academic visits were to Department of Astrophysical Sciences, Princeton University, USA, Institute of Theoretical Physics, University of California, Santa Barbara, and Institute of Astronomy, University of Cambridge, 1987, Canadian Institute of Theoretical Astrophysics, and Inter-University Center for Astronomy and Astrophysics. I now request Professor Rajaram to please deliver his talk.
Thank you, Professor Srivastava. I think I'm not muted now, right?
Yes, sir. You are very much
Okay.
audible.
Yes, sir.
Okay. So you would have gathered from this introduction that I've been involved in many things, but I do want to emphasize that my absolute favorite subject, thanks to very distinguished teachers, is optics. And I welcome this opportunity to talk about this favorite subject to this audience. There are many distinguished members of this audience, including people like Professor Gatak, who has a textbook on optics, Professor Mani, who I believe is writing a textbook on optics, and I'm sure there are many others who have a deep insight into the subject. So what I will be doing is to try and address myself to the majority of these 515 participants whom I see, who I'm told would be physics teachers. Okay. And teachers of physics typically at the 12th standard level. And my familiarity with that actually comes from my involvement in the NCERT textbook project, which was mentioned by Professor Srivastava. And I have to say that when one is in the research institute, one is unaware of the problems faced at that level. But writing this textbook and having everything we wrote criticized by teachers at NCERT was a very good experience. And then following that, for the last 5 years at Azim Premji University, we welcome to our undergraduate program students from different parts of the country with different levels of preparation at the 10th standard level. And so my own education in physics at this level is relatively recent. So therefore, I will not presume to tell the members of this audience who have much more experience how they should handle their task. And it is a very difficult task that they are handling. My plan is therefore to follow the sequence of topics as in the textbook, but try and enliven it with some history, some pictures, discuss some conceptual questions, all of which may be a little complementary to what one has to do to complete the syllabus. Alternative ways of looking at known results. And there are many applications of optics, and I have at least put in one or two which may not be familiar to everyone. And most of all, I'm interested, and I'm sure the teachers amongst you are also interested, in that small subgroup of students who are very curious, very questioning. They're not necessarily the highest scoring students. The highest scoring students probably spend all their time solving lots of problems for the IIT exam, right? But we also meet these other students, and I think we have to take care of them also. And they sometimes raise interesting questions. So I have tried to raise some of these questions that I've heard over the years and try and give my own kind of. So a little bit of history here. These two great figures of optics from the 17th century. In fact, people have said that Huygens would have been regarded as one of the greatest physicists and mathematicians, but for the misfortune of being a contemporary of Isaac Newton. I want to make a distinction between Huygens' construction and Huygens' principle. Okay, Huygens' construction is really something in geometrical optics. It tells you how to construct wavefronts and construct rays which are perpendicular to the wavefront, and then explain the well-known facts of geometrical optics, which I have listed here. And one unusual case of geometrical optics, which we will not talk about today, is the double refraction calcite crystals. It used to be in the NCERT textbook, but I think in the interests of reducing pressure, it's been removed. But all of you are no doubt familiar with it. Again, he understood the geometry of wavefronts, but reading his book, there's no hint of the cause, which is polarization. And that had to wait another 120 years. It's also interesting, and in preparation for many lectures on optics, which I've given earlier, I went through both the books, Treatise on Light by Huygens and Optics spelled with a K by Newton. And there is no mention of wavelength or phase in his book. Okay. Now let's look at Newton. Well, Newton's rings are named after him. And that's actually a very clever way of creating very thin films. To put a convex lens on a plane surface, you can get all values of thickness depending on how far away you go to the center. And putting white light, or sunlight usually, on these, he noticed the colors. And he drew his own conclusions from the colors. People say that he was an advocate of a particle theory of light. Well, he used the word corpuscle, and his corpuscles had some interesting properties, entirely theoretical, proposed by him, because he noticed that these colors, one ring could be blue, and then you would get rings of other colors, and then blue would come back, and so on. So he realized that there's some property of these corpuscles which varies periodically with the thickness. He called it fits of easy reflection. Being a rival of Huygens, he did not use the word waves, but he actually gave numbers in inches, if you read his book. So in some sense, he had something like a wave theory of light. And in the case of double refraction, again, he doesn't, of course, talk of polarization. There was no concept of electromagnetic fields. But he does realize that this shows what he calls a property of sides, which means that there is some property in the transverse plane. So I would come, and if you come to diffraction, the earliest experiments were before Newton by this person in Italy, but it was then repeated by Newton and others. In fact, one of the nice experiments which anyone can perform, which was performed by Gregory at the same time, is to take the feather of a bird and look at the sun through it. Okay, and you see beautiful colors, beautiful pattern. In any case, he was aware of this property. So I would submit to you that opposite to what we are taught in the textbooks, the greatest practitioner of geometrical optics in the 17th century was Huygens, and the greatest practitioner of wave optics without actually believing in waves was Newton. Now let's try and appreciate some of the features of this Huygens construction. We usually do the case when the speed of light is constant, unless you get to a different medium. But I have now chosen a case where the speed of light is increasing as you go from the top of this figure to the bottom. So you've drawn a circle of one radius here, a bigger radius here, and a bigger radius here. Right? And therefore, you can see that the next wavefront is tilted with respect to the previous wavefront. And the next one is still again tilted. So when you draw the perpendiculars to these wavefronts, in the limit that you make the spacing very small, you get a kind of continuous curve. Okay. Now, the big question which students ask is, why are you neglecting all the secondary waves coming from all the other points, all right, and only taking the secondary wave coming from this point when you are interested in what is happening at this point in the next wavefront? Now, one cannot answer that question without bringing in the wave theory of light. And Huygens himself, since he did not have a concept of wavelength or phase or interference, he simply seems to have remarked in his book that these wavelets are all very weak and they're very strong here only when they arrive simultaneously. Well, it's almost simultaneous, right? Because if you start a wave from here, it has to travel diagonally, whereas this travels by the shortest path. But the difference between these paths is second order. It's a cos theta kind of factor, right? So to a first approximation, a number of waves originating from all these places arrive simultaneously here. Okay. So the justification ultimately comes from wave optics, that the interference is constructive here, and most of the contribution comes from this point. But we also learn an interesting byproduct, that this Huygens construction is also a good way of finding the shortest path between 2 points. Suppose I want the shortest path from here to here. This perpendicular is clearly the shortest distance between these two wavefronts. This is the shortest distance between these two. This is the shortest distance between these two. You try to go by any other path, you will easily be convinced that it's a longer path. So you can also look upon the Huygens construction as implementing something that we don't mention in the 12th syllabus. Maybe we should. It's called the principle of least time, which was proposed before Huygens by Fermat, okay, who was primarily a mathematician, but who had a brilliant insight into optics. Okay. So really, in the textbook, we need not bother to, if we are just following Huygens, we need not bother to draw all these spheres. We can just draw perpendiculars to the wavefront whose length is proportional to the velocity or inversely proportional to the refractive index. And then we can say the wavefront advances perpendicular to itself at the local speed of light. Okay. And I'm particularly interested in the case where the speed varies. And as an example, I would like to choose this textbook topic, the mirage. We normally teach it as we divide the medium into layers and treat it as a case of total reflection. But from Huygens' principle, one can look at it somewhat differently. You can see that some rays are reaching you from this point directly, and some rays are reaching you after coming close to the ground and coming back. So the rays are sketched here. So this is the ray which reaches you directly. And here, let us assume, and it's a good assumption, that the refractive index is more or less uniform. But very near the road, the refractive index is lower near the road because the temperature is higher. And at the same pressure, it means the density is lower, so the refractive index is lower. Okay. So from Huygens' point of view, we saw how the wavefront curves. And interestingly, from the Fermat principle point of view, even though this path is longer when measured in meters or centimeters, it may be shorter in terms of time because it's taking advantage of the greater speed of light, the smaller refractive index being closer to 1 in this layer. Okay. So that's just a few remarks on Huygens' principle and the connection with Fermat principle, which may be of interest to, as I said, that group of students, certainly of interest to teachers because teachers will always stay ahead of their students. Now, even without worrying about interference and diffraction, the mere existence of a wavefront enables us to realize properties of geometrical optics, which would have been rather difficult to understand purely by tracing rays. So one of the principles is that if you start from some source, goes through a complicated imaging system, could be many lenses, mirrors, whatever it is. And let's say it's a good imaging system. So when you come here, all the rays focus to an image. Could be inverted, could be magnified. Don't worry about that. But basically, we have rays coming out of this point, which means it's a spherical wavefront. And then at some later time, that spherical wavefront has become a converging spherical wavefront and focused here. So the mere fact of Huygens' construction tells us that the total time taken to go from here to here should be the same no matter which ray you take. Now you could try, well, intuitively you can say, yes, this ray has a longer geometric path, but if this had been a simple convex lens, it would have spent less time in glass, whereas this ray would spend more time in the glass. Okay. And this is an extreme case of the Fermat principle of least time, where every ray actually is neither a minimum nor a maximum because the function is a constant, okay, on all rays. And this is a very powerful principle. You can use it to derive many other results in geometrical optics, okay. While working in Wikipedia for the sake of this lecture, again went into a little bit of history, and one of the sites had this picture. Of course, this picture is there in many textbooks, but what I like about this picture is that Young himself made the sketch when he first spoke of his lectures in public in the Royal Society in 1803. And this illustrates what his thinking must have been like, perhaps inspired by water waves. And notice that from each of these slits, he is assuming that the rays or the waves go in all directions, okay? So the slit itself is a very oversimplified object. It's really more like a source than a slit. And that is the way we teach. Even in the 10th standard, we teach it as 2 point sources. And what the nice thing about this picture is that without any calculation, you can see where there is constructive interference and where there is destructive interference, okay? So for example, if you look at the 2 sets of waves, here they overlap, which means they have the same phase, right? Let us say the darkened portion happens to be a peak. So here there's a peak falling on a peak. Here there's a trough falling on a trough. So in both cases, along this entire line, you have constructive interference. Whereas here you find that the peaks are falling on troughs, and therefore along this line, you have destructive interference, okay? So these are really the dark fringes. And we learn several things from this picture, even without doing much calculation, that the fringes don't exist only on the screen. They exist in 3-dimensional space, And the job of the screen is only to make the fringes visible to you. And there's a very subtle point about fringes. If you look carefully at this bright fringe and the next bright fringe, and you look at these little diamonds, you see that the point where the troughs occur in this bright fringe coincides with the point where the crests occur. This is the point, troughs occur, coincide with the point where the crests occur. So you could ask a student the following question. It's a very unfair question. If I put a screen here and made one hole here and one hole here, both on bright fringes, and did an interference experiment, what would I get in the center of that? And the answer is, interestingly, you will get a dark fringe. Okay. So, and depending on the level at which one is teaching, sometimes you may have to go to a school and in a few minutes explain to a much younger class what is Young's experiment. So then my advice would be to take along 2 combs and hold them, and immediately you can see the fringes. And in this context, of course, it has nothing to do with the wave theory of light. It has to do with superposing any 2 periodic patterns. And long ago, it was observed in a very fine form of silk, which was given the name Moire patterns. And Moire patterns are easily demonstrated using combs. And once you look out for Moire patterns, you will see them everywhere. And I have already emphasized for you these properties. One can also be more quantitative. We can draw a diamond of this Moire patterns, and you can easily convince yourself that the distance from here to here is lambda over theta, which is equivalent to the formula which has been drilled into our head, so much so that I remember it. If you wake me up, I'll remember it's capital D into lambda by small d, right? But this brings in things like the distance of the screen and the separation of the slits. Why I like this formula is it tells you the most relevant thing is the angle subtended by the 2 slits at the screen. And if you go to some other point, that angle could change and the fringe spacing could change. Okay. And as I said, the subtle point about phase reversal, we can also use this kind of picture to discuss what happens when many wavelengths are present in light. Okay. And there is this standard saying, so I'll first try a picture. It's not a very good picture. I'm sure many of you will be able to make better pictures. And one of the difficulties I have in making such pictures is I belong to that 10% of the male sex who are colorblind. Okay. So for the colors, I rely on what the software tells me. If it says it's green, I assume it's green. Okay. So this is, let us say, the central fringe of Young's. So any wavelength will give you constructive interference there because the 2 paths are equal. And though the figure doesn't bring it out, you have green sitting on top of red, sitting on top of blue. But now, because the fringe separation depends on lambda, the next bright fringe of blue occurs first, green next, and orange last. Okay. So the moment you go away from the central fringe, the bright fringe gets separated with respect to color. And then as you go more and more away, the separation increases. And in fact, since I have chosen only 3 wavelengths here, they will have a kind of LCM. And you'll again find that they will fall on top of each other, but with different numbers. The order of the fringe will be different, but you may get a mixture again. Now, seeing this in Young's experiment is rather hard. Okay. Right. So this is the explanation I gave you. But the place you see it very well is in seeing the colors of thin films. And if at all one has the time and the patience, I would say an introduction to wave optics could start by blowing a soap bubble. Right? So this is, of course, taken from the net. In fact, this is a point to express my eternal gratitude to Wikipedia, right? And all of us, I think. Soap bubbles have the property that under gravity, the soap solution slowly descends down. In fact, that's why they ask you to add glycerol to the soap. So the viscosity increases and therefore the soap film lives for longer. Okay. And the interference is now between 2 waves, which are more or less traveling in the same direction because they're reflected from the 2 sides of the soap film. Okay. And the uppermost part where the thickness of the film is very small, much less than the wavelength of light, is actually dark. Now, this itself is something interesting. because if you have reflection with a very small path difference, right, because the thickness of the film is very small, you assume that it should be constructive interference. Therefore, you should see a bright reflection here. So, on the other hand, intuitively, you will say that the film is very thin. It should hardly reflect at all. And that's the correct intuition. And therefore, the phase of the reflection is different at the two interfaces. And there is a 180-degree phase difference. And that is why a thin layer is almost black. And then as you come toward the bottom of the soap film, the thickness increases. And if you go, let us say, if you go, say, 500 nanometers, that's not a bad compromise between, say, 400, 500, 600. So all of them will more or less show constructive interference, and you will get a whitish color. But if you go still further, now the shortest wavelengths will start to get destructive, and they will cancel out. So you'll be left with the longer wavelengths. Then the longer wavelengths will cancel out, and blue will reappear, and so on and so forth. So there's a very nice sequence of colors as you gradually increase thin films. This was noticed by Newton and discussed in great detail in his Optics. But I would like to go back to the phenomenon of partial reflection. Right? You have an interface, and you don't have to go to a soap film. From very ancient times, people have gone and looked down in a well or in a tank or in a river and seen their face, but they have also seen the bottom of the river, which means that some of the light comes back and some of it gets through. If you believe in a particle theory of light, which Newton did, it's not impossible to explain it, but you have to do something statistical. You have to say that on the average, 50% of the light is getting, say, refracted. Actually, for water and air at normal incidence is more like 5% or even less. Glass and air is 5%. But at oblique incidence, it can become 50%. But the important point is that for individual particles, they either have to get transmitted or reflected. So you have to bring in some kind of probability. And of course, we know that Newton believed in a particle theory of light, and that was abandoned. And who is the person who brought back the particle theory of light? Not really Max Planck, but actually Albert Einstein, right? And in his very first paper, he is forced to bring in particles to explain the photoelectric effect. And in fact, that is the next chapter in the NCERT textbook, after wave optics, I think, the wave nature of matter, photoelectric modern physics, so to speak. But then how do you explain interference phenomena? And actually, Einstein doesn't say much about that in his paper. He just says we have to believe in these particles. But later on, when quantum mechanics was created, people realized that these particles are not the particles we're used to. They are particles whose behavior, whose probabilities are governed by some mathematical functions which look like waves. Okay, and that we do say a little bit even in the 12th standard. But it's interesting that just thinking of partial reflection and reflecting on it forces you to think deeply about the nature of light. Okay. Now, I have said diffraction by a single slit, but actually it's a diffraction by a straight edge. So I should really have said diffraction by half a slit. And this is the phenomenon which was studied in 1660, so around the time of Newton, but not by Newton, by an Italian priest, in fact. It's interesting how much interesting research was done by priests. They had good libraries in their monastery, and if they became senior enough, maybe they had some spare time. But so Mendel, for example, a priest created his theory of heredity. Now, near the edge of a shadow, under very careful experimental conditions, one actually sees some bright and dark lines. And they are not equally spaced. And quite quickly, as you go away, you just see brightness on this side and darkness on this side. So which is why this phenomenon is not discovered for a long time. And Wikipedia has kindly superposed a graph here, which shows the variation of intensity becoming very small in the shadow, becoming almost constant away from the shadow, and actually oscillating and having its prominent maximum. Now, Grimaldi actually observed colors as well because he was using sunlight. Okay. And the word itself means breaking into pieces. So people didn't understand what the implication was for the nature of light. They said maybe this light passes the edge, it's a sharp edge, and maybe it breaks into pieces. Okay. Now, one of the things I have been asked often by young students. What is interference? What is diffraction? I mean, why do you use different terms for it? They come in the undergraduate optics textbook. They are even different chapters. And I think this is partly a problem of history and a problem of terminology. So in all cases, we have a wave coming from a source. If you're very far away from the source, it's almost a plane wave, almost a set of parallel rays. And then it encounters some obstacle. The obstacle could be a screen with one hole in it, two holes in it. So really, these are all the same phenomenon. Okay. And if you wanted a single name for it, we should not use either interference or diffraction. We should use scattering, which incidentally also means breaking into different pieces. So I would say the general phenomenon is scattering when light wave encounters any kind of obstacle. But there are some particular cases which we would like to talk about, which are simpler. As far as Young was concerned, a very small hole was just like a news source. But people who actually studied bigger slits and so on realized that something interesting is happening there. Now we are seeing fringes here, and we are all familiar with the fringes in the Young experiment. Okay. But in this straight edge, what is interfering with what? Okay. So this is an interesting question. And notice that interference between two equal waves would actually give you a very dark fringe here and a very dark fringe here. That's not happening. It's also clear that the angle between the two waves is not remaining constant because the spacing of the fringes is not constant. So this is some strange kind of interference. What is it? Okay. And what is interesting is there are two answers to this question. Okay. Sorry, this last part was supposed to be a surprise, but please ignore it. So Fresnel, inspired by Huygens, said, here is an obstacle. This thin line is a plane wave coming from infinity. You are sitting somewhere, either here, away from the shadow or inside the shadow. What you have to do is do an integral. In fact, the integral is called the Fresnel integral, okay? Where you add up contributions, and if the perpendicular from this point to the wavefront lands on the wavefront, not on the obstacle, then according to the argument we saw earlier, there'll be a dominant contribution from here. But if you're somewhere here, then there's a lot of cancellation between the secondary waves which come from all these points, and therefore it very quickly becomes dark. So that is the mathematical explanation given by Fresnel. And that's what you'll find in all the textbooks. Okay. Now, some of the textbooks, and the truly encyclopedic textbook on optics is the one written by Born and Wolf. Okay. Does include an alternative point of view, which I think is interesting. I'm not saying you should teach it in the classroom. It might confuse people, but you might get the odd student who would benefit from knowing more than one viewpoint. And historically, Young, somehow he was a more intuitive person. He said, there is this edge. So when the light waves hit the edge, probably a wave starts from the edge. Okay. And he explained what is happening by saying this edge wave, therefore, in this diagram would be like a circle like this. So you have this circle, and then you have the direct beam, and the two interfere. And you can see that between a circle and a plane line, the thickness keeps varying. We saw that in the connection with Newton's rings. And therefore, the fringes also, the fringe spacing also keeps changing. Okay. And then when you come here, you only see the edge wave. Of course, he had to postulate some interesting properties for this edge wave. The edge wave intensity would have to fall off as you go away from this edge. But that's the explanation he gave. And this was placed on a better footing by Sommerfeld and some of his students. And in particular in India, C.V. Raman was a great devotee and advocate of this point of view. So he himself put some of his own best students on it, K.S. Krishnan when he was in Kolkata and Ramachandran when he was in. And they worked on something called a geometric theory of diffraction, where basically you interfere waves coming from the edge. Okay. And this was placed on a sound mathematical foundation by Keller. Obviously, I won't tell you all that, but you will readily appreciate that sometimes if you're lucky, an integral, if it if it is can be written as d of some quantity, then you can integrate by parts, and you will be left with a contribution from this boundary and a contribution from far away. So that's how the edge wave theory of diffraction works. Okay. So both are right. Yeah. And it's a matter of convenience. Today, of course, diffraction theory is also important even in defense science. So to give you one example, if you want to detect a plane by radar, you send a radio wave and it encounters this obstacle. And of course, the plane is much bigger than the wavelength. So different parts of the plane will send back secondary waves with different wavelengths. And you would like to know how strong is the signal coming back to you. And this cannot be solved easily by 12 standard methods or even MSE methods. So you have to go to a computer, but even the computer would find it very difficult to integrate over the whole plane. And therefore, people do use the geometric theory of diffraction when they do electromagnetic scattering from large objects. Equally, if you belong to the other party, which where you own the plane and you don't want it to be detected by radar, then you do similar calculations, but you keep modifying the nature of the plane and the kind of paint you put on it and so on to minimize the wave which goes back to the radar side. Okay, so that is a little bit about the importance, technical importance of diffraction theory. But I would also like to say something about its astronomical importance. Okay. So this is the picture. It looks exactly like a straight edge diffraction pattern, but this was taken at radio waves in 1962 in Australia by astronomers. They were looking at an object which had an interesting name. It was just called 3C273, which simply means that C stands for Cambridge, 273 stands for the number of the object, because large number of objects were discovered by Cambridge emitting at radio waves. And 3 stands because they published their results in multiple volumes, and 3 is the third volume. Okay, so when astronomical objects become very large, they don't get nice romantic names like Pleiades and so on. They get names like 3C273. So they calculated that the moon, which moves in the sky relative, as you know, the moon visits 27 stars in a month, so it moves relative to the stars. They calculated that it would cover up 3C273, and they said this is a great opportunity. Let us observe the diffraction pattern. Okay. And they were able to observe the diffraction. This looks like the textbook diffraction pattern, except because of the longer wavelength and the greater distance to the moon, this whole phenomenon occurs over a minute, which means quite a long length scale. And this is deflection, right? If you see time is going this way, right? This means it has gone behind the moon. Immersion, right? Now, actually, because the moon is a circle, the direction of the straight edge is not exactly the same in these two patterns. Now, what is the purpose of their experiment? Not to verify the age-old theory of straight edge diffraction, but to understand the position and the structure of 3C273. So suppose 3C273 had been double source. You would have seen 2 such patterns. And in fact, here they saw a bump which told them that in addition to this source, there's another source. Okay. And most important, they got a very accurate idea of the position because they know exactly where the moon was. And that, see, with radio waves, your resolving power is very poor. We will talk of the resolving power of a telescope toward the end of this talk. Okay. But in this case, your resolving power comes from the edge of the moon. Okay. So, and historically, once they located accurately the source of these radio waves, at that time, the nature of the object was completely unknown, because to understand the nature of an object, optical astronomers take pictures, take spectra, but if you don't know where the object is, you can't do that. But once they gave this position, they realized it was very important, so much so they made 2 copies. When it was sent by plane, in case one of the planes crashed, they wanted to make sure the other copy went to California, where the great telescopes found an object which is very interesting in its own right, called a quasar. Okay, it's very far away, very bright, and very compact, sitting in the center of a galaxy. And I'm sorry, I can't tell you more about it. Okay. So inspired by this, Professor Govind Swarup in 1966, only a few years later, in fact, maybe even earlier, sitting in Tata Institute of Fundamental Research said, look, these people were able to do 3C273 because it's a bright source. But we would like to learn about a large number of much fainter sources, which are much further away, and we will learn about cosmology. So he said, we will build a telescope whose main use will be to observe this. Okay. So that was the concept behind the Ooty radio telescope. It started operation in 1970. It is still working, which is pretty amazing. Okay. So you have diffraction of radio waves at a wavelength of 90 centimeters by the edge of the moon, and the positions and structure of hundreds of sources were found. In fact, Swarup's first student who published the first cosmological telescope results from this telescope is Vijay Kapahi, who unfortunately passed away quite young. Professor Swarup happily has recently celebrated his 90th birthday. He's very active. So it's Vijay Kapahi who gave the name for these two events as Ayaram and Gayaram, which I think this audience will appreciate. Okay, any audience in India will appreciate. So I have to show you a picture of this telescope. There are a lot of clever things about it. It's huge in area. It can rotate about this axis to follow the source. And you can also pick up unknown sources because you only follow the edge of the moon. Whatever source it comes up will give you a pattern. So not only did they do hundreds of sources, most of these sources were unknown. So it's a great tool for discovery. Of course, later on people built bigger telescopes, and then this telescope was used for other purposes, which is happening right now. In fact, Govind Swarup himself had a joke that the Ooty group is the only set of astronomers who are professional lunatics, right? You know, the word lunacy for being mentally unstable actually comes from the moon, because people earlier used to think that it's the phases of the moon which cause mental disturbance. Okay. So anyway, I had to tell you about the Ooty radio telescope because actually in my own master's studies, educational tour to this place was very inspiring and helped me to take to astronomy. And I could not have anticipated at that time that I would move to NCRA and, you know, be responsible for a large group which was building an even bigger radio telescope. Now, of course, there's an interesting way of looking at the resolving power of a microscope, which was given by Abbe. I should have put a dash here. Interestingly, he spent his entire life working in a factory. But in those days, factories also had very good research departments. The factory is called Carl Zeiss. The location is Jena, which is in Germany. And they used to make the best microscopes and telescopes, and, you know, best optical instruments. Even today, I think a Carl Zeiss binocular is considered very good spectrograph. Now, he gave an interesting way of understanding the resolving power of a microscope. He said, how would you test whether a microscope is good or bad? I would put a periodic object, something like a wire mesh, okay, at the focus of the microscope. So I've drawn something like a wire mesh. That's why I've drawn a dashed line. But, and you illuminate it from this side and you look at it in a microscope. Now, you get an image which is a copy of this. And how is that image formed? According to wave optics. So according to wave optics, a periodic object like this acts like a diffraction grating, which all of you know. It has an undiffracted beam and a first order beam and a minus first order beam. Okay. And then these three beams again interfere after being combined by the objective lens. Okay. And they recreate this periodic pattern, except of course, you know, this distance in a microscope is very short, and then the next image is formed quite far away. So this angle will be smaller. And when the interference occurs at a smaller angle, this periodicity will become larger. We saw lambda over theta. So you'll get a magnified image. So the magnification and imaging by a microscope could be understood by this argument, which is purely based on wave optics. Okay. But then Abbe tells you that, look, suppose these two diffracted beams miss the objective lens, right? Then you're simply going to not see any periodic pattern at the focus, and you would have failed to resolve the object. So all you need to do is to understand the formula for the diffraction grating. So if small d is the spacing of the object, then we know that sine theta, I mean d sine theta is 1 lambda for the first order. Okay. Of course, if you put more orders, you will get a better image, but let's say at least the first order. Huh? So sine theta is lambda over d, and this should be less than sine alpha, where alpha is the angle subtended by the objective lens at the focus. So again, the beauty of this argument is only deals with essential quantities. You're not talking of the diameter of the lens, you're not talking of the distance, focal length, nothing, just angles. So therefore, in order to see an image of this periodic object at the next focus of the microscope, its spacing d has to be greater than lambda by sine alpha. So that is the resolving power of the microscope. Right? So it's of the order of the wavelength, and of course you better make alpha as large as you can. Right? So that's why good microscopes are expensive, because you have to make lenses which have angles which are large. So, angle could be 45 degrees, 60 degrees, and so on. And the usual optics we teach students in 12th standard assumes that sine theta is equal to theta. So, of course, these lenses are designed by much more sophisticated computer programs. You also have to make sure all colors come to the same place. You have to make sure that an object at a different point will also give you a sharp image. So that is the powerful field of applied optics. But here is a simple argument for the resolving power of a microscope. So let me then try and give you, again, at the same simplified level, an argument for the resolving power of a telescope. So please ignore this orange line. As I said, I'm sure you see it as orange, and the software told me it's orange. I see these both roughly as the same color. And this is the green wavefront, okay? You can either think of a wavefront, or you can think of a set of parallel rays. And you can either think of the parallel rays converging to a focus, or you can think of a set of spherical wavefronts converging to this focus. So that is the image of one star. Let's call it the red star. The green star. Now we have a red star, which is displaced by some small angle theta with respect to the red star. Okay? So that means, let us say that even if these two waves agreed in phase here, by the time you come here, there will be a path difference of d into theta. So now we are going to ask the following question. If light comes from this star, will there be some, of course, the correct point where this wavefront will interfere constructively will be somewhere here, okay, where all the paths will be equal by the same principle of lenses that we saw in the beginning of the lecture. However, when you come here, but you are still thinking of this orange or red wavefront, the paths are unequal. But if the difference in paths is less than the wavelength, you will still get some light here, and the images of the two stars will overlap. So to be on the safe side, you would like the difference to be at least one wavelength. So then you will get a kind of complete cancellation here, right? And the two images will be different. So d into theta has to be greater than lambda. So this is the resolving power of the telescope. Okay. Now I come to probably the most difficult set of questions. I found it difficult to write when I wrote the wave optics chapter. I found it difficult to defend when I came to Delhi and the teachers came and questioned me. And even today when students come, you convince students about wave optics, and then they say we should be seeing interference everywhere, right? What do we tell them in the textbooks? We tell them when the two frequencies are different, there's no interference. That's what we say in the optics chapter. But what do we say in the acoustics chapter? When the two frequencies are different, they produce beats by interference. So it is an interference pattern, but it depends on time. That's the point. And in fact, there are experiments which have been carried out with lasers in the middle of the 20th century, in fact, latter half, where you actually have generated fringes from two lasers, okay, whose frequencies might be slightly different, but you take a very quick photograph. Then we have this concept of independent sources or incoherent sources. So my favorite example would be I have two lasers but maybe I connect them to two different plugs, and the two different plugs are fed by different power stations. Okay, so they're completely independent. And then we simply tell the students they don't have a steady phase relationship. So even if you get some fringes, the fringes will move around. And this is a bit, I mean, it's not wrong, but maybe at least for the more critical and curious students, we could take the following point of view that light beams always interfere in classical optics. Okay, but if the frequencies happen to be different, the interference pattern will depend on time, and if it's not a single point source, but each source will produce its own interference pattern, and again, the sources have some phase relationship, right? But that will in turn keep changing with time, and then we say that our measurements are usually an average, and therefore we don't see. And this is a better point of view. Because if you work at radio waves, then the technology really enables you to probe spatial scales much shorter than the wavelength, and scales of time which are much less than the period. In fact, when I went to the GMRT observatory, and if I mentioned a time like a nanosecond, the engineers there would say that, yeah, that's a very long interval of time, right? Because they work at much higher frequencies. The other point I have to mention is that if the intensity is very weak, okay, then this wave description, I won't say it's wrong, but you have to understand it much more, because in a single wave, you may not have many photons, okay? So, I mean, that's a more subtle topic. So my first wish is that your students don't raise it. And if they do raise it, then I would refer them to the textbooks on optics, either those which have been written, or which are being written, which would have a section clarifying how, even in a quantum theory, you can see some interference phenomena. Okay. So I would like to conclude now, and I should really thank all of you for listening and giving me an opportunity to talk about a favorite topic, which is optics. I hope that came through. I also hope that this wasn't completely, my repetition was what is in your textbook, okay? And I'd be happy within the constraints set by the large numbers to take questions at this point. Thank you all again very much.
Thank you, Professor Rajaram Nityanand, for the enlightening lecture. Now I request Dr. Yogesh Kumar sir. Now I request Yogesh Kumar sir to moderate the question answer session. And again, I am requesting all the participants to write their question in the question answer box only. Yogesh sir.
Thank you, sir. Thank you so much, Singal sir. Before proceeding toward question and answer session, I would like to extend my gratitude to our speaker, Professor Rajaram sir, for his wonderful talk. Sir, your talk was really very lucid and useful for our participant. And here I can see a lot of queries in the question and answer box. So the session is open for question and answer. So here is the first question asked from Vikram Singh Chauhanji. From daily life activities, apart from color pattern, in on CDs and on oil films, which example of interference or diffraction on a large scale can be put in front of students?
I think the feather is not usually mentioned in, and this is available, especially now that birds are moving around freely and dropping their feathers. You just pick it up, and of course, sun being a slightly broad source, you will still see something. You might damage your eyes. But if you look at, for example, a sodium lamp or a mercury lamp is even better because you'll see many colors. So I think a feather is very nice. And Yogesh साहब आप लक्षद्वीप में है कि अंडमान में है? कुछ बहुत सुंदर दिख रहा है आपके पीछे.
जी सर. Okay, thank you. Next question is from Gokul Krishna ji. How the color bands on screen differ for interference and diffraction? In what order we can see if figure form on the screen?
Okay. Yeah, as I said, the distinction between interference and diffraction is somewhat historical. Okay. For example, if you look very carefully at Young's experiment, you have two single slits. Now, each slit will produce a diffraction pattern, right? But if the slit is very narrow, the angle of that diffraction pattern, which is given by lambda by small d, will be, or lambda by a, will be very wide. So these two wide diffraction patterns overlap on the screen, and that combination we call interference. But really, it's one physical phenomenon. So regarding the order of colors, this is actually quite nice. I should have mentioned actually a little bit in the answer to the previous question. There are other nice examples of diffraction in nature. One is this precious stone called opal, OPAL. Okay, has a periodic arrangement of holes, and it shows brilliant colors. And you can ask, is the color due to some chemistry of dyes, or is it due to interference and diffraction? And the simple criterion is that the colors due to interference and diffraction will change with angle. So if you look at this opal, or you look at the soap bubble, and you look at it from different angles, or illuminate it from different directions, you will see the colors changing. Whereas a chemical color will usually remain the same. Now, regarding the order of colors, this is a very standard thing that a prism will deviate the violet rays the most, whereas a diffraction grating will deviate that the least, because sine theta is lambda over d, and if lambda is smaller, theta is smaller. So I hope that gives at least a brief answer to the question.
Sir, next question is from SL Roda sir. He's asking, how can we explain polarization by scattering or reflection at the school level on the basis of wave theory?
Okay, I think if I remember right, the original poster said Wave Optics Part 1. So Professor Srivastava has very, I think, kindly, he originally proposed interference, diffraction and polarization. But being greedy, I said, no, ये नहीं चलेगा. एक session में सिर्फ interference और diffraction हो सकते हैं, and polarization we'll keep for another session. So Professor Srivastava, can you confirm?
Okay. I think he's...
Next lecture.
It's okay, sir.
Okay, sir. Next question is from Dr. Kalyan Dey. Can you shed some light on the topic spatial and temporal coherence?
Okay, without using those terms, I think I did it, but very briefly, because this whole lecture was rather brief. So let me try something. Let me see if it works. There is something. I'm looking for something called whiteboard. Some versions of Zoom have it. So then that allows me to draw. But okay, just give me a minute. Huh? Give me.
Yeah, sure.
Sir, you come to the share screen, then you get the whiteboard.
Whiteboard है क्या?
Yes.
इधर तो नहीं दिख रहा था तो मैं.
Share screen.
Okay.
Whiteboard है sir.
है.
Yes, sir. When you share the screen, then there will be a whiteboard option.
हाँ, maybe I didn't do that.
Yeah.
Share screen.
I have to hit the share screen first.
Yes, sir.
Is there a whiteboard option?
Yes, sir. Yes, sir.
Yes.
कहाँ पर है ये?
Sir, while sharing your screen, you will have the option.
Okay, but it doesn't matter.
And with what to write?
No.
Sir, by finger you can write.
Yeah. And actually, I have a small tablet. Anyway, I'll do it in MS Paint. So the question is spatial coherence and temporal coherence. So if I had to give a very quick answer, I would say that if you have, a monochromatic plane wave is a very ideal form of light because it's infinite in size, right? Plane waves. Okay. A monochromatic plane wave is infinite, whereas any realistic model of light will have a finite size. Okay, so therefore, what I would like to do, right? So what we would really like is a wave packet. So it's a finite region of space in which you have some waves, right, with some wavelength. It has a finite extent. Now, basically, I mean, again, this is slightly, so it doesn't really have plane waves going strictly in one direction. In fact, to get a wave packet of size capital D, yeah, in the transverse direction, you have to satisfy this condition, which we have already seen, that D is some lambda divided by theta. So if you superpose plane waves with angles theta and an average wavelength lambda, you will get a wave packet of size lambda by theta. Then there is also this longitudinal size of the wave packet, and that is obtained by superposing different frequencies. Okay. So if you have, suppose this is the frequency axis, this is energy versus frequency, and power is something like that. So you have some mean frequency omega, and you have another frequency width, which is delta omega. So then, if you only have two frequencies, you get beats. If you have continuous range of frequencies, you get a wave packet. So now, natural light consists of having a large number of such wave packets, because natural light, there is always a spread of angles and always a spread of frequencies. So now a simple-minded way of understanding spatial coherence is this wave packet could now get divided at a half-silvered mirror or at two slits, something like that. But at the point where you look for the fringes, the same wave packet must arrive at both places. So if there is too much of path difference, if the path difference is more than this, you will be trying to interfere two different wave packets which have no permanent phase relationship. Likewise, if the two beams are displaced in the transverse direction by more than this, so that is spatial coherence, and this is longitudinal. They are sometimes called transverse coherence and longitudinal coherence. So a condition of interference from a source of a finite size and a source of a finite spread in frequencies, or what engineers call bandwidth, okay, is that you must calculate a longitudinal coherence length and a transverse coherence length and make sure that these are respected in your interference setup.
Kalyan for his answer. So next question is from Parvati. She's asking, please explain the absence of intensity of background envelope of secondary wavefront mathematically when we construct secondary wavefront.
This is in which example? Which example was she referring to? That part I didn't catch. Absence of?
I repeat the question. Please explain the absence of intensity of background envelope of secondary wavefront mathematically when we construct secondary wavefront.
Okay, I think I understand now. Yeah, the question is sometimes asked. Maybe I can use the same. So I draw a secondary wave. Sorry, not a very good circle. And this is the backward propagation. I think that is an age-old objection to Huygens principle. Well, see, we should remember that Huygens created his principle where he understood waves at a physics level, but the current mathematics of waves, wave equation and so on, was not developed. It was developed much later. So in some sense, you should regard whatever he stated in his book, which unfortunately is completely repeated in our textbooks nearly 400 years later, 300 years later, is just a set of postulates. So he simply postulates that you have to add all these, but it's also true that later people did try to give a mathematical formulation. And one of the mathematical formulations, again, itself not very rigorous, is given by a person called Kirchhoff. So this you could look up in any advanced textbook on optics, or even a textbook of electrodynamics like Jackson will have it. So in that, it turns out that the secondary wave has an intensity 1 plus cos theta, okay, where theta is angle with respect to So when you go to the backward direction, it becomes exactly 0. But I would say this is the mathematical answer. And I much prefer the answer given in Feynman lectures, even though it's a very extreme answer. See, in volume 1, he has not yet introduced Maxwell's equations. Nevertheless, he has chapters from 27 to 34 on optics. And they are quite rigorous because it's based on electromagnetic theory. So he simply asks the reader to accept the formula for radiation by a point charge, explains what are electric and magnetic fields. And with that minimal input, he develops all the principles of optics. So how does he handle diffraction problems? He handles them very physically. So you don't have, see, Huygens' idea that vacuum itself can be the source of secondary waves is a little difficult to swallow. You can do some mathematics which makes it look like that. But the point of view of Feynman is, I have a source. I have some metal, maybe with holes and so on. If I go anywhere, the electric field which I see must be electric field due to this current, oscillating current, and electric field due to the oscillating currents in this metal sheet. And from that principle alone, so these oscillating currents will also produce some field which is on this other side. Interestingly, if you have a metal plate without a hole, okay, then all the wave gets reflected. And in Feynman lectures, he makes an important point that don't simply say the field is 0 here. You have to prove that it is 0 by adding up the field due to this and the field due to all that. So I think this is the deepest way of understanding diffraction. And interestingly, this is also the way that the modern computer codes work. So you take the field, say, of your radar set, take some distribution of currents over the aeroplane, and the difficulty in the computer codes is how to calculate this distribution of currents. But once you do that, so then all these artificial ideas of secondary waves and all can be removed. Unfortunately, we are not able to do this at the higher secondary level. And therefore, we have to make lame excuses for absence of backward waves and why we choose only this point and so on. So at least to convince yourself, I would say read those chapters of Feynman lectures, volume 1.
Yeah, right. Shall I move back to next question, sir? Okay. Next question is from Sandeep Kaurji. She's asking, the explanation of diffraction is never so convincing for a student. Please guide in this.
I think I would only agree with this statement that the Huygens principle, though historically very important, it gives correct results. It led to some approximately correct mathematics, which is the Fresnel integrals and all that which I mentioned. But if you are going to be very critical, you will find holes in it. So, except for my answer to the previous question, well, I think there are two routes one can take. One can appeal to common observation, like the student knows that sound consists of waves, okay, and you know, you can hear people even when you cannot see them, right? In fact, that's the whole idea. When you want to overhear a conversation, you stand on the other side of the wall or something, and that you hear them, right? So the fact that energy does not only travel in straight lines and can go around a corner or go through a hole and spread out. And then you have the ripple tank, where all these phenomena can be nicely demonstrated. So in fact, in a wave theory, the most difficult thing to understand is rectilinear propagation. Rectilinear propagation is easy to understand in a ray theory. In a wave theory, you have to do a more complicated argument, right? So suppose I have a wave coming here. In a ray theory, it's very natural that the intensity is 0 here. In a wave theory, you have to actually calculate a sum over all these points and show that there is a lot of cancellation here. So I would rather say, start from an extreme wave point of view to the student, and then say, look, it's very easy to understand waves spreading out, interfering and all that. And you spend all your time and effort in understanding rectilinear propagation. And by the way, the proof should not be too effective, because the rectilinear propagation is only an approximation. When this is very wide compared to the wavelength. If this is small compared to the wavelength, you don't have rectilinear propagation. So I think this is what I would do if I had to talk to this student.
Next question is from Sabri Sarkar. Is it possible to produce interference effect between the O ray beam and E ray beam, which are separated by a calcite crystal from a unpolarized incident beam by recombining them?
Okay, nice question. I could say let's deal with it in the next lecture, but okay.
Next question, sir.
Yeah. No, this relates to O and E. Yeah, maybe I can take it in the next lecture. Yeah.
Okay, fine. Next question is from Survi. Why we draw arc in Huygens principle, we can draw a straight line.
Okay. I presume that are you referring to these arcs? These arcs are really parts of a sphere. And the reason why you draw this is, let's think of it in a very simple way. Imagine that there is some event which occurs. In fact, in astronomy, it could be the explosion of a star, right? So then the light from that moves out at the speed of light. So therefore, it forms a sphere. Okay, it forms a sphere. Now, so that's why it's natural. If you assume there is a source here to form spheres, and I only drew small arcs. So in fact, let me. Yeah, sorry, there are two arcs here. Think of them as some successive wavefronts coming at different times. Yeah, so that's the reason why I drew these arcs. So I think the straight line that you may be thinking of are the rays. Okay. And at least between two wavefronts, you're approximating it by a straight line.
देखो ये अंकल कितना बढ़िया से कहाँ बैठा है।
Can you hear me, sir?
I can hear.
Yeah. So shall I move to next question, sir?
Yes, please.
Yeah. Next question is from Chesai. She's asking, please explain the shift in the interference pattern when the source slit is not equidistant from two slit in Young double slit experiment.
Okay. Yeah, for simplicity, we take the source to be here in most discussions. So this is equidistant from the two slits. But I think it is important to realize that you will get the interference pattern even if the source is somewhere here. So now, even coming from, okay, sorry about that. So you have one path coming from this slit and one. And now these two are not equal because this is not lying on the perpendicular bisector. So then, see, the interference pattern occupies the entire screen, okay, and the part which is illuminated anyway. So now we can ask, where is the bright fringe going to be where all the wavelengths interfere constructively? That will be, so maybe if I call these points A, and then I have some S1, and I have S2, right? And then I have to find a point P so that, you know, AS1 plus S1P equals AS2 plus S2P, right? That's what you have to find. So if I move this down, okay, what does it mean? That this path is longer. Therefore, to compensate, this path has to be shorter. That's why I have to move this point up. Yeah, as simple as that. Now, of course, you can actually work out the geometry and check that if I move this down by some angle, this moves up by the same angle. But in a way, it's similar to the argument for a lens, no? If you think about it. Because I already told you that I have a lens, and if I take a point on the axis, all these paths are equal and they interfere constructively at the image. Now, suppose I move this down, then all of us agree the image moves up. But it's still true that all these paths are now equal, right? Okay. Yeah, that's my answer.
Okay, okay, sir. So now I can take last two questions due to the paucity of time. Next question is from Anil Kumarji. He's asking how to show that width of different fringes are different in diffraction. Shall I repeat the question?
Yeah. How to show that?
How to show that width of different fringes are different in diffraction.
See, again, I want to distinguish between diffraction by a straight edge and diffraction by a single slit. If you take a single slit, let's talk about a single slit first. I will draw this usual graph, which shows the intensity as a function of position on the screen. Right? I mean, that's what the graph looks like. Sorry, intensity doesn't go negative. That's just, they get weaker and weaker. Now, in the single slit pattern, actually, these are equally spaced. If you look at the formula, they are equally spaced. But it is true that from here to here is double this separation. I mean, it's given by the formula sin x by x. And sin x by x, if I look at it, it's of course maximum at the origin, and then it has pi, and then 2 pi, and so on. It's 0 at all these points. Sin pi is 0, sin 2 pi is 0, and likewise 0 at these points. So only this gap is double. All the other gaps of size pi, and this gap is double of size 2 pi. Now, if you talk of diffraction at a straight edge, so let me draw another figure. Let me take a new figure. So this is the straight edge, and I'm going to use the Young's theory of straight edge diffraction. Fresnel theory means you'll have to evaluate Fresnel integrals, which is a bit complicated, at least for a short lecture like this. So according to Young, you have these plane waves, and the plane waves continue. Except, I mean, he's not very clear what happens. He said the plane waves come only up to the edge. See, this is an intuitive theory. It's not a... So when you have interference between this plane wave and this spherical, actually cylindrical wave coming from the edge, right? You can see if you have interference between two plane waves, you get equally spaced fringes. But you have interference between a spherical wave and a plane wave, you don't get equally spaced fringes. So it's really the same reason that Newton's rings are not equally spaced. You would have noticed that the formula for Newton's rings also, they are not equally spaced.
Yeah. So, sir, next question, the last question, I think, for this session, is from Shalu Kapoor ma'am. She's asking, please tell some ways to show diffraction and interference pattern in school labs to the students.
Okay. See, I always like things that students can do by themselves. And see, in school labs, nowadays, the fashion is to use lasers. The lasers are very cheap, right? So you take the laser and you just point it to the edge of a blade or something, and you go to the wall. You don't even need to make the room very dark, and you will see many of the things. But there are some disadvantages in this. One disadvantage is that if you have a class of 20 students, I can guarantee that at least one of them will want to point the laser in the eye of some other student. Okay, so you really have to be careful. So this is important, actually. You can do damage. The second is in a way, a laser is not a good preparation for optics because a laser will give you interference with any path difference. Okay. So what happens is, in addition to the fringes which you want to exhibit, you will see all kinds of other fringes because the laser light bounces off different things. You will see what are called speckle patterns, and you will have to explain all that to the student. So therefore, maybe I'm being a little old-fashioned, that I was brought up on sodium light, mercury light, but today most city lights are sodium light. So I would say, if you look through a piece of cloth, preferably synthetic cloth, at a light, you can just place it directly over your eye or over your specs. You will see a beautiful two-dimensional diffraction pattern. Then CD, of course, CD was mentioned. There are some, these are, so a quick demonstration. Of course, this is really, we're demonstrating diffraction grating. If you want to demonstrate diffraction through a small hole, again, I would say if you take, this requires a little more care. You may have to take a thin metal sheet of the kind which is used to wrap medicines, make a small pinhole in it. And again, if you make a small pinhole and look at very, let me explain, actually little explanation needed. So let's say we have a small hole. We have a very distant sodium lamp, and therefore we get a diffraction pattern. So let us say that diffraction pattern is really different intensities at different angles. But what I'm telling you is put it in front of your eye. Now your eye is actually really an instrument which converts angles into position on the retina. So therefore, in the laboratory, what you would do is you would put a converging lens here and you would project it onto a screen. All that you are doing is you're projecting it onto your retina. So many people don't realize this, that you can take diffraction gratings or feathers and place it right next to your eye. Right? And they will produce plane waves, which the eye will focus on your retina. So that's what I would suggest. And anyway, nowadays, people don't shave with those old-fashioned blades, and they're also dangerous. You cut yourself with them. So I think feathers, pieces of cloth, or pins are not so dangerous. So making pins, small apertures. I think the problem with lasers and computers and so on is that they make things too easy, right? So then students get bored and they say, okay, tell us something new. So if you can't tell them something new, you should tell them something old, because they don't know that either, right? Only people like me will remember, some of these old-fashioned ways of doing optics.
Okay, thank you so much, sir, for handling the queries of our participants. In case participants have more queries, they can directly mail to Professor Rajaram, sir. The email ID will be shared in the chat box. Thank you so much, sir, for your enlightening session. Now I would like to hand over the session to Tiwari, sir, for proposing vote of thanks. Tiwari, sir.
धन्यवाद योगेश जी। परम आदरणीय आज के मुख्य अतिथि हमारे प्रोफेसर राजाराम नित्यानंद जी, गैलेक्सी ऑफ स्टार्स ऑफ फिजिसिस्ट, पद्मश्री श्री डॉक्टर JS राजपूत जी, प्रोफेसर मनी जी, अजय घटक जी, मैं सबसे पहले आप सभी का हार्दिक धन्यवाद करना चाहता हूं। और जिस प्रकार से इस सेशन से पहले डॉक्टर असवाल ने, डॉक्टर अजय घटक जी ने फिजिक्स को आसान बनाया, उसी प्रकार आज डॉक्टर नित्यानंद जी ने इतने अच्छे तरीके से डिफ्रैक्शन इंटरफियरेंस को समझाया कि उससे हम लोगों को ये एहसास हो गया कि साइंस हमारे चारों तरफ है और घर में ही है। सर ने एग्जाम्पल दिया था कॉम्स का, कि दो कॉम्स को लेकर हम डिफ्रैक्शन पैटर्न को समझा सकते हैं। सर, रियली इट इज न्यू फॉर ऑल ऑफ अस कि आपने इतना अच्छा उदाहरण हमें दिया डिफ्रैक्शन का, सिंपल, जिसे हम घर पे भी कर सकते हैं। आपने ज्योमेट्रिकल थ्योरी ऑफ वेव्स हमें बताई, एज वेव्स के बारे में हमें बताया। हालांकि हम में से बहुत सारे साथी ऐसे हैं जो 12th तक की क्लासें लेते हैं, लेकिन अगर बेस मजबूत होगा, कंसेप्ट अगर 12वीं तक की क्लास में ही अच्छा हो जाएगा, तो नो डाउट कि फिजिक्स को बहुत आसान मानने लगेंगे। अभी धारणा यह है कि फिजिक्स बहुत मुश्किल सब्जेक्ट है, लेकिन आप लोगों से बातें करके, जो हमारे 3, 4, 5 सेशन हुए हैं, इससे पहले प्रोफेसर राजपूत जी ने भी करीब 3 साल पहले प्रोफेसर वेद रत्न लेक्चर में हम सबको अपने अनुभव शेयर कराए थे। वो उनसे भी हमें बहुत फायदा हुआ। तो ये जो गैलेक्सीज ऑफ स्टार्स ऑफ फिजिसिस्ट है, इनके पास आकर हमें लगता ही नहीं है कि हम अभी अध्यापक है, हम अपने आप को अभी भी स्टूडेंट ही मान रहे हैं, और आप लोगों से सीख कर इसको हम आगे की तरफ बच्चों तक पहुंचाएंगे। सर, बहुत बहुत आपका धन्यवाद कि आपने बहुत ही सहज शब्दों में और डाउन टू अर्थ आकर हम सबको फिजिक्स के कंसेप्ट, खास तौर से डिफ्रैक्शन और इंटरफेरेंस के, हमें बताए, हिस्ट्री से लेकर और लेटेस्ट टेक्नोलॉजी तक। मैं धन्यवाद करना चाहूँगा दिल्ली साइंस टीचर फोरम का कि वो आज हमारे साथ कंधे से कंधा मिलाकर इस प्रोग्राम में है। डॉक्टर PN वार्ष्णेय, कन्हैया लाल जी, डेविड जी, RA गोयल जी और बाकी और सदस्य दिल्ली साइंस टीचर फोरम के, उन सबको मेरा हार्दिक धन्यवाद। मैं अपने IAPT जो एग्जीक्यूटिव कमेटी है, अपने प्रेसिडेंट प्रोफेसर VP श्रीवास्तव जी का, IAPT RC1 का बहुत बहुत शुक्रगुजार हूं कि उन्होंने मुझे ये मौका दिया कि मैं वोट ऑफ थैंक्स दे सकूं। मेरा धन्यवाद डॉक्टर ओम प्रकाश जी को, सूरज प्रकाश जी को, जिनके मार्गदर्शन में हम चल रहे हैं, प्रोफेसर खंडेलवाल जी को, जो फाउंडर प्रेसिडेंट हमारे रहे हैं। इसके अलावा मैं धन्यवाद देना चाहूँगा गिरी भारद्वाज जी को, सीमा वत्स जी को, प्रोफेसर सहजवानी जी को, राजीव त्यागी जी को, मनोज कौशिक जी को, अजय गर्ग जी को, डॉक्टर ओम प्रकाश शर्मा जो हमारे एक्स प्रेसिडेंट हैं। इसके अलावा अनिल कुमार जी हमारे पैनलिस्ट हैं, उनको भी मैं हार्दिक धन्यवाद देना चाहूँगा, हमारे एक्स प्रेसिडेंट हैं। रवि भट्टाचार्य जी को, रमनीक कपूर जी को, R भारद्वाज जी को, जयवीर सिंह जी को, रमेश कुमार जी को, SK गोयल जी को, आप सभी का बहुत बहुत धन्यवाद। मैं यहाँ पर अपनी स्पेशल टीम, जो हमारी ये टेक्निकल टीम देख रही है, प्रोफेसर भंडारी, डॉक्टर सिंघल, डॉक्टर योगेश जी और डॉक्टर पूनम जैन जी, जिनके बदौलत हम ये सब वेबिनार कर पा रहे हैं। ये दिन रात लगे रहते हैं और हर आयोजन को सफल बनाने में ये अपना घर बार भूलकर इस काम में लगते हैं और इसको सफल बनाते हैं। मैं सभी पार्टिसिपेंट्स का, जो 408 के करीब हमारे पार्टिसिपेंट्स हैं, उन सभी का मैं धन्यवाद करना चाहूँगा कि उन्होंने प्रोफेसर साहब को सुना, और मैं ये आशा करता हूँ कि प्रोफेसर राजाराम जी, नित्यानंद जी ने जो आज हमें इतने आसान शब्दों में और सहज शब्दों में फिजिक्स का डिफ्रैक्शन और इंटरफेरेंस समझाया है, उसे हम अपने बच्चों तक पहुंचाने की चेष्टा करेंगे। आज के हमारे गेस्ट ऑफ ऑनर डॉक्टर JS राजपूत जी का भी मैं आभारी हूं कि उन्होंने आज हमारी प्रार्थना को सुना और हमारे इस दिन को बहुत शुभ बनाया। डॉक्टर अजय घटक जी, प्रोफेसर HS मनी जी, आप लोग हमारे इस प्रोग्राम में आए, आपने हमारे इस प्रोग्राम की शोभा बढ़ाई, उसके लिए हार्दिक अभिनंदन, स्वागत। और हम आशा करते हैं कि आपका प्रकाश लगातार हमें इसी प्रकार मिलता रहेगा, जिससे कि हम और अधिक उत्साहित होकर इस तरह के कार्यक्रम आयोजित करते रहें और देश बच्चों के हित में हम आगे बढ़ते रहें और उनको फिजिक्स की तरफ मोड़ने के लिए, इंटरेस्ट क्रिएट करने के लिए हम सदा प्रयासरत रहें। मैं यहाँ पर एक बार पुनः, पिछली मीटिंग में भी मैंने कहा था, सूरज प्रकाश जी का स्वास्थ्य ठीक नहीं चल रहा है। हम सब प्रार्थना करें ईश्वर से कि वो जल्दी से ठीक होकर हम सबको ज्वाइन कर सकें। और इसी के साथ मैं आप सभी का हार्दिक धन्यवाद करता हूं और विशिष्ट रूप से दिल्ली साइंस टीचर फोरम का, कि जो हमारे साथ कंधे से कंधा मिलाकर काम कर रही है। आपका सभी का बहुत बहुत हार्दिक धन्यवाद और शुभकामनाएं। थैंक यू वेरी मच। मैं आगे की कार्रवाई के लिए डॉक्टर पूनम जैन जी को आमंत्रित करता हूं कि वो कार्यक्रम को आगे बढ़ाने की कोशिश करें। धन्यवाद।
Thank you, Tiwari sir. Since this is the end of the session, so I seek permission from our respected president, Professor V.P. Srivastava, to sign off this meeting formally.
Yes,
May
please.
I, sir?
Yes, please. Yes.
Thank you, sir.
Thanks, everyone.
Before signing off, I once again thank you to all the panelists, participants, our distinguished guest, the speaker of the day, the persons who have joined from the DSSTF forum for making this webinar successful. I also like to thank all the participants personally on behalf of IAPT RC1. Thank you, everyone. Stay home, stay safe, and moreover, stay connected. Thank you. Sir, now I am signing off this meeting formally.
Thank you. वो अपने आप साइनिंग ऑफ कर रहे हैं।